Hello and good afternoon, CTS267 Section 840 students for the Spring 2017 semester at Anne Arundel Community College. This is the CCNP TSHOOT course, and this afternoon's video tutorial is going to be a quick review, and we're going to augment a little bit here the information from Discovery Activity number 2, and this is the last discovery activity before we get into sort of the trouble ticket scenarios, and we're going to be looking at troubleshooting connectivity. So we're going to be spending some time here on PC1 initially, so let's hop on to PC1 real quick. And as you can see, we're already in privilege exec mode, and so they're asking us to ping to 10.10.50.2. And let's see what happens here. So as you can see, we don't have any connectivity right now. So we're sending out ICMP echo requests, but we're not getting any replies back. In fact, if I were to say debug IP packet, I think it's detail, there it is, debug IP packet detail, and let's rerun that ping command, we should see some additional activity here. In fact, we're specifically going to see the ICMP type, right, which is going to be type 8 here. And it looks like we're seeing the type 8 code 0, table ID, and then type 8 code 0, type 8 code 0, type 8 code 0. So how do we decipher what these codes mean when we're doing a debug? Well, let's pull up the, it's a really good document here. If you search for this document ID, simply Google 12778. And again, hasn't been updated in a while, but it's definitely a good document. If we scroll down a little bit here, the Cisco PDF is going to show me, and you can see here, ICMP type 8 corresponds to the echo message, right? And let's come down a little bit further. So here's the ICMP type, and here's 8, right? It's the echo that we're sending, and we're not receiving back an echo reply. So we're sending out that echo request, but you can see we're not getting anything back because there is no reachability. And so this is a very nice document. It shows you the ICMP types, and then it kind of gives you a breakdown as to the literal, what that type represents, what it stands for. And right below this table, we're going to be taking a look at the ping table here shortly as well, because you see some interesting output with the ping command sometimes. It's always good to know what those mean. So we're trying to ping 10.10.52, and we're not having any luck. But let's take a look here. Let's go back to the job aids and take a look at the diagram here, and let's see 10.10.52. What is 10.10.50.2? Well, it looks like router 4 is 10.10.51, and so then it's PC2. So we're trying to go from PC1 over to PC2. And again, from a troubleshooting perspective, always follow a process. So if I ping, probably the first command that I want to run after that ping is going to be show ARP. And let's see what we see here. Well, we've got my address, right? So this is going to be our address, which is why you don't see it aging out. And we have an entry here that tells us to go to AABBCC002100, right? So the layer 3 information, right, in the ARP cache, which is the IP address, 10.10.52, that IP that we were pinging, we now have an ARP cache entry here that didn't exist before, and it tells us to go out Ethernet 00 and specifically to that MAC address, right? That layer 2 hardware address, which, since we're pinging off of our local network, this is probably going to be our default gateway. If we look at the diagram here, you can see that we come up to router 1 and then go to router 2. So if we were to pull router 1 up here, and we were to say show IP interface brief, you can see we've got the 10.10.10.2. So let's say show interface Ethernet 00. And sure enough, right, we use this layer 2 information here, along with a little help from layer 3 with the IP address. But at layer 2, this is what we're looking at, right? Because we're directly connected here to this router, and this is our next hop. So if I'm on router 1 and I say show ARP, or I could say show IP ARP, you can see that we do not have an ARP cache entry. What if I ping 10.10.50.2? And let's see what happens here. Okay, so from router 1, it looks as if I can reach the address. From the PC, I could not. So let's go ahead now and say show ARP again. And you can see we don't show an ARP table entry for 10.10.51, but if I were to say show MAC address table, let's see, what do we see? Do we see anything? No, on the router we don't see anything, right? So how does the router do it? Exactly, that layer 2 read-write information is where? If I say show IP ceph, we see the outgoing interfaces, but what do we need to take a look at? So we need to say show adjacency, right? And this is going to show me the outgoing interfaces, okay? And from this, we can take a look and we can see that we have, doesn't look like a default route here. Let's say show IP route. Is there any default route? No, there's no default route, but we're learning it from OSPF. Whoops, sorry. We're learning it from OSPF. So for that layer 2 information, if I say show adjacency detail, right? And we have this in the same shot here, so it's being learned from OSPF from router 2, right, or from 10.10.22 out Ethernet 0.1. So when I come over here and look at Ethernet 0.1, I've got my source and destination MAC, and then the 800, which is going to represent IP, right? So here's where my layer 2 information resides on the router, right? So we don't say show MAC address table on the router. We say show adjacency detail, and this is going to provide me with the layer 2 information I need to make the decision. So, but right now, PC1 doesn't have any connectivity to PC2. So what they're asking us to do is let's source this from a different address. So on PC1, what if I were to say ping 10.10.52, but then source it from Ethernet 0.0. And again, remember, the outgoing interface that it takes according to the RIB, that is going to be the source of the packet. So even when I do this, you can see that we're getting back the periods still, and we're seeing that type 8 code. So the ICMP echo request is going out, but we don't have a reply that's coming back in. And again, you can see the success rate 0 out of 5%. So we've got no connectivity. But again, remember, when I say show IP interface brief, when I ping this Ethernet 0.0 interface, that's going to be the source of the ping, because that's the outgoing interface. That's the interface that it's going to be taking when it goes off of PC1. Okay. So now let's go ahead and let's see what they're asking us to do here. All right, so we've been pinging 10.10.52, and now it's asking us to ping it again. Ping from R1 to PC, oh, from router 1 to PC2, sorry. And we just did that. So we know that it works from router 1 to PC2 when I ping 10.10.50.2. Sorry, I thought they were saying PC1 and it shouldn't work. And they have an example of it working. I'm like, wait a second, we haven't fixed anything yet. So from router 1, everything works great, right? From PC1, it's definitely broken. So we come back to the topology here, and you can see we make it to router 1 just fine. So let's come up to router 2 and say show IP route for the 10.10.50.2. All right, so we have a static route with an administrative distance of 1, and it says that we are going to go to 10.10.40.2. So if I were to say show IP route to see the whole routing table, here is the static that we've got entered here on router 2. So router 2 has a static route, show run section route, and there it is to the 10.10.50 network, telling us that we will go to 10.10.42. And we're going to choose the static route over any OSPF learn routes. Why? Exactly, that administrative distance, right? So the administrative distance, whoops, sorry about that. The administrative distance of that static is going to be 1, and the administrative distance of OSPF is 110. So even if we were learning it as an OSPF route, we're not going to install that into the RIB. So again, it's the static route that sends us over to router 4. So let's cruise over to router 4. Right, we're just kind of following along now. So 10.10, what was it sending us to here? Router 2, 10.10.42, which must be, take a look at router 3 here, see if that 10.10.42 is on here. Show IP interface brief. And it is. There's 10.10.41, and the 10.10.42 is going to be router 4's interface that connects up with router 3 here. So on here, if I say show IP route 10.10.50.2, so how is router 3 learning about this route? Exactly. Router 3 is learning about it via OSPF. And it's got a metric of 20, administrative distance of 110. And it's an intra area, right? So it looks like we're all area 0 here. So let's go ahead and say show run section OSPF. Let me check this real quick. Yeah, so it looks like everything's in area 0. And so, but what does it tell us? It tells us that the next hop is 10.10.42. So now we just kind of walk over to router 4, and let's take a look. So we go from user exec to privilege exec. We say show IP route 10.10.50.2, and we're directly connected. Now remember, the ICMP echo requests, right, when we're pinging, they not only need to be able to make it all the way over to the destination, but the destination needs to have routing information to get back. So in other words, it's likely that we are pinging, and let's pull up our drawing tool. It's likely that the ping is going this direction, right? And it's getting to router 4, and it's conceivable that we're making it all the way here to PC2. But when PC2 goes to send the return traffic needs to know the routing information back to PC1. So let's see, let's log on to PC2 here. Whoops, let's clear that out. Let's log on to PC2 and let's see if we were to say debug IP packet detail. Let's see, do we see anything when we run that ping over to 10.10.52? Does PC2, aha, right? So this is interesting now, right? Because now we're seeing the echo request, but we're also seeing the echo reply, right? So now we get these ICMP type 8 code 0. That's my request, but now I've got ICMP, where's it at? There it is. And you can see what happens here when it's coming, or it's going, it's ICMP echo reply from 10.10.52, trying to get over to 10.10.10.1, remembering that that is PC1, right? But you can see we've got some error messages popping up here. So it doesn't look like PC2 has information to get back to PC1. So let's check it out here. So we'll say all for undebug all. And right now what we want to do is we're going to say trace to 10.10. And not 50.1, where is it? 10.10.10.1, correct? Yeah, 10.10.10.1. And we'll say, oh, it doesn't like the numeric argument, so it looks like we're going to have to let it try to resolve it. So we'll talk about that numeric argument. And as you can see here, we can't get anywhere, right? I don't have any information, so we'll say Control-Shift-6. Whoops. We'll say Control-Shift-6, and let's come up to router 4. So let's see, router 4, which would be the default gateway for PC2. If I say show IP route 10.10.10.0, subnet's not in the table. Let's see, does Ceph have something? Show IP Ceph for 10.10.10.0, and we'll just leave it at that. So we have no route. If I say show IP route, you can see that we don't have any of the required routing information to make it from router 4 over back to router 1, right? And router 1's all the way over here so that router 1 can then forward the traffic onto PC1. So what do we need to do? Well, there's a couple things we could do. If we check router 3, we're running OSPF, right? And so that's probably going to be our solution. But let's take a look here. Show IP route for the 10.10.10.0. Yeah, so router 3 also doesn't know about the 10.10.10. So if 3 doesn't know about it and 4 doesn't know about it, let's see if router 2 knows about it. Show IP route for the 10.10.10.0. Yeah, so the subnet isn't on routers 2, 3, and 4. So we've got some options here, right? We could put a static route on router 4, pointing to router 3, a static route on router 3, pointing to router 2, and a static route on router 2, pointing to router 1, or we could do what we should be doing at the CCNP level, which is recognizing, hey, we're running OSPF here. Let's jump on router 1 and say show run section OSPF. And as you can see, we don't have a network statement for the 10.10.10. So let's go ahead, jump into global config and say router OSPF1 and put a network statement in here for 10.10.10.0.0.0.255 as our wildcard mask, and it's going to be in area 0. So now when I hit enter, I come over here to router 4 and I say show IP route. Do we see it? Well, we don't see the 10.10.10 yet, and there it is. Took a second. We were a little quick. And you can see it's only been in the rib for 1 second. But now we have the routing information that's going to be required. So now if I were to say trace over to 10.10.10.1, take a look now. Much different story. And as you can see, we actually get to the destination. So now let's come over to PC2 and let's check. Is it going to work from PC2? Trace to the 10.10.10.1 and take a look at that. Right, works like a champ. We go to router 4, router 3, router 2, router 1, and then we make it to our destination. So everything works, but again, remember, we have to have that routing information in order for things to work. So now we're going to talk about the GRE tunnel running between router 2, and let's say show IP interface brief, and there we go. You see that tunnel 0 interface. So show run int tunnel 0. And you can see here that the OSPF cost is put at 5. The interface is in area 1. There's our IP. We've got our tunnel source and our tunnel destination. So 70.2 is going to be up here on RA. And so that should be Ethernet 00. Should be that next hop address. Let's take a look. Show IP interface brief. And sure enough, Ethernet 00 is 10.10.70.2. And so let's take a look at show run interface Ethernet 00. Right, and you can see, so that's going to be the next hop. But let's take a look at, and again, that's tunnel destination. So the tunnel IP, show run int tunnel 0. And you can see right here, we've got our tunnel source, tunnel destination. That this interface is in area 0. And so now what we're going to do is we're going to be taking a look at testing connectivity with PING and TRACEROUTE. But what we're going to find is that we may run into some issues here. And let me take a quick look. And I believe they want us to change the way that we're going here. And in order for us to do that, we're going to have to dump that static route. And I'm looking to see here, they don't tell you to dump the static route. Let's see. Okay, so they definitely want you to go through the tunnel. So let's do this. On router 2 is, I believe, where we have that static route. Show run include route. And there we do have that static route. So let's get into global config and say no IP route for the 10.10.50.0. And that's going to be 255.255.255.0 to 10.10.40.2. So we're removing that static route. So now when I come over here to router 1 and I say do trace to 10.10.50.2, we should be going out the tunnel interface. Yeah, so interestingly enough, it doesn't tell you to pull that static route, or I didn't see it to tell you to do that. But you definitely have to pull that static route out because this would be the more preferred path going through the tunnel. And so as we run the traceroute command, you can see that we go up to router 2, which is 10.10.22, and then we go across that tunnel interface. We come down to the interface on router, is it 3? Yeah, so we're basically going this direction now that we've removed the static route. So we're going up and around and coming this way to get from PC1 to PC2. All right, so let's clear our screen here. And let's see. So the traceroute definitely shows us what we wanted to see. So now we're going to experiment with the ping command. And they want us to set the DF bit, right? And there's a reason for this. And it's that GRE tunnel. Remember, the IPMTU is 1500 bytes by default. But when we start adding encapsulation, and the encapsulation is going to be that GRE header that gets added onto the GRE tunnel interface. And that's 24 bytes, right? So 1500 bytes is typically what it is, but we're now using 24 bytes of that for the GRE header. So let's go ahead and do ping, and whoops, let's get out of here. So we'll say ping 10.10.50.2, and the size we're going to say 1476, and we're going to set the DF bit. Right, and so we can see that the ping works and that everything works great because, again, that's 24 bytes less than the ICMP, which is, again, by default going to be 1500. The problem is, if I were to say set it to 1477 and I'm setting the don't fragment bit, that's what that DF-bit says. It says don't fragment these large packets. Then we get this M period M period M. So let's walk back over here to this document where it tells us right away, right? Super easy to take a look at this code and say, okay, hey, we couldn't fragment because, again, the reason we couldn't fragment the IP packet is because I said DF-bit, which is setting the do not fragment bit. I'm basically telling the router, I know you can fragment it if you wanted to, but I'm telling you not to fragment it. So if it's not going to fit in the MTU that we have, which is 1476, you're going to drop those packets, right? You're not going to be allowed to fragment. And again, there we go. Whoops, sorry. I want to go back to the web browser. And again, the reason we're seeing that is because we're going through this GRE tunnel here. So 1476 will work, because that is 24 less than 1500. And so then we can accommodate the additional GRE header on top of the 1476 bytes that are going to be going across as it stands right now, right? Because we're forcing it down to 1476. So what if I were to say 1477, but I remove the DF bit? Now what's going to happen? Is it going to work? Absolutely, but it's fragmenting the packets to do it because we've only got 1476 bytes in the MTU that are available instead of the 1500, so it's going to be forced to fragment those packets. So if I were to come to router 2 here, and let's see what router 2 says. Let's say do debug IP packet detail, and let's see if we see anything interesting here when we run that command again. Let's go ahead and say size, we'll say 1499, right? And so let's come over to router 2, and we do get some information here. And let's let this, and actually let me say do, whoops, get back in here into the window. So we'll say do you all, right? So basically undebug all. We want the debugging to stop. And so we can see now where the packets were coming in from the source 1010. I'm sorry, there's a multicast. Where are we at here? Where did I kick this off? Oh, here we go. I think it kicked it off right around here. And we were coming across the tunnel interface, packet routed to the adjacency, sending full packet. Hold on one second. I'm looking for an indication that we fragmented. Yeah, I don't see, and maybe I'm looking right at it, but typically we see that it's being fragmented to go out that tunnel interface. And you can see that it's routing, it does route out the tunnel interface, right? But it doesn't show us that it's being fragmented. And so we'll have to continue to look at that because it should say in here that we're being fragmented. So again, the reason that we can get away with this is because we're not saying don't fragment. So again, if I were to come up here and say size 1499 and set the DF bit, you can see we get the M back from the ping command because the router's not able to fragment it. And in fact, let me say, let's do this, debug IP packet detail. I think I may have been looking at this backwards. Let's do it here with the DF bit. Yeah, packet, there it is, failed, right? Packet routing failed. And the reason that it's failing is because the DF bit is set, the do not fragment bit is set, therefore the router is not going to fragment the packet. And so the routing is going to fail, right? But it'll succeed and everything will work fine if I take the DF bit off. And you can see everything goes through fine and we don't see that anything is failing, right? And protocol 89 is OSPF. And you can see that sending full packet, no problems there. Okay, so that is the ping command, and that's using some of the extended options, the size, and then setting the DF bit, kind of giving us an idea that, hey, the tunnel interface that we're going through, we can't get everything through that we want without having to fragment things. So there's another way to do this. Let's turn off debugging, is we could use the extended ping. I can simply say ping, and we're going to go to 10.10. Whoops, 10.10.50.2. Repeat count is going to be 1. Datagram size, we'll leave it 100. Timeout in seconds, we'll say 1. Extended commands, right? So here's our extended ping. Source interface, we'll just leave that as the default. We don't have any TOS type of service. Now, set the DF bit in the header. Yes, we want to do that. And what we're going to do, this is called a ping sweep. So we're going to start at a certain size. We don't want to validate the reply. I don't care about the data pattern. And what we're going to say is sweep range of sizes. So yes, I want to do a ping sweep. So we're going to start at 1400 bytes, and I'm going to walk all the way up to 1500 bytes. Now, we know that this is not going to work because we're going through that tunnel interface that will only allow packets of 1476 bytes. That's going to be the max, and below, right? So if it's smaller than 1476, we're fine. But anything over 1476, it's not going to work because that GRE header is going to come into play. So we hit enter, and we do the sweep interval and take a look, right? And so what you'd have to do is count out these exclamation marks, you know, 1401, 1402, 1403, 04, 05, and you're going to come right up to here. Whoops, you're going to come right up to here. Or, if you take a look here, success rate is 76%. So it's very easy to say, oh, so 76 of the 100 ping packets, or I'm sorry, 76 of the ping packets made it through. So if we started at 1400, and 76 made it through, the maximum would be 1476. And that's a lot easier than sitting here trying to count all of these, or trying to work your way backwards counting the M's. It's much easier to take a look and say we started at 1400, 76% made it through. So that means the first 76 packets made it through. So that would be our 1476, and that, again, that's our maximum size. That is our ICMP. Now, what's typically done on some tunnel interfaces, depending upon what kind of encapsulation you're using, right? So if you're doing DMVPN, you're obviously using multi-point GRE. You're probably using IPsec. You could be in tunnel mode. You could be in transport mode for your transform set with the tunnel. And so typically what happens is on that tunnel interface, and the tunnel sits between 2 and 1. So on the tunnel interface, if I went into interface tunnel 0, what I would say is IPMTU 1360 and IPTCP max. Yeah, it should be IPTCP. It's not showing it here. Oh, adjust MSS. There it is. Adjust MSS. And what are we doing? So we did. Oh, the MTU's 1360. No, IPMTU. I'm confusing myself here. So the adjust MSS should be 1360 because we need to account for the 40 bytes of the transport header, and then the IPMTU is 1400. And that gives us a pretty substantial range. It basically shrinks the MTU down, but it ensures that we have a smaller MTU size to accommodate all of the additional headers, right? And so that's a common practice with DMVPN, is you're going to set the TCP adjust MSS down to 1360 and the IPMTU to 1400. That gives us 100 bytes of encapsulation headers. So if there's IPsec header, you're going to have your GRE header, and those things are all going to add up. So we want to make sure that we give enough room. And again, the reason that there's a difference here between the TCP adjust MSS and the MTU is because this TCP, the segment size, remember that IP header, we're talking about 40 bytes. So we want to make sure we push that down to 1360 so that we stay below the 1400 to accommodate all the additional headers that we may have. All right, so now it's asking us to basically check connectivity, and says we have layer 3 connectivity, and what you can do is you can use the Telnet utility to find out if ports are open, right? So I can simply say telnet 10.10.50.2, and then I can put in, I'll do a question mark here, you can see we can put in a port number, right? Or, as you can see here, I could type in www. So I could say www to see if we can connect, and in fact, we can, right? So we're able to create a socket between router 1 and the PC2 HTTP server, because again, it is servicing things on port 80. So if I were to type some commands in here, you see we get bad request, right? So I typed, I just hit those characters and typed something in, and then the HTTP server came back and said bad request, and then the connection gets shut down. So again, this shows it's open, so we'll put something in there, and we get bad requests. So again, this is another way to check to see, hey, am I able to reach a specific port somewhere here in this topology? All right, well, this is going to wrap up Discovery Activity 2. And again, just to sort of recap, we took a look at doing and running the traceroute command when we were coming this way, as well as the ping command, and seeing that we have to have connectivity for those ICMP echo replies to get back, right? That type 0. And it's going to be the ICMP type 8, which is the echo request, that's going to be going outbound, and then the echo reply, which is a type 0, and we'll say this is type 8, that we need to make sure that we have reachability in both directions, or else it's going to appear that we don't, that something is broken in between. And we also saw that all we needed to do was add an OSPF route here to router 1. Then we took a look at the IPMTU. We have a GRE tunnel here. And remember, with the GRE tunnel, and we'll draw it out real quickly, I've got my layer 2 header, right? And remember, your layer 2 header is going to be all of your physical address information, right? Your source MAC and destination MAC, right? And so that's where these live. Source and destination MAC, and that's where these live. And then we're going to have the layer 3 information. But when we're doing GRE is going to add in 24 bytes of overhead that allows us to encapsulate the IP packet, right? And so we have to shrink the MTU with our ping command. It's going to fragment, right? But if the don't fragment bit is set, we saw that it failed for anything greater than 1476 because we've got this additional 24 bytes. And so that's why we say IP MTU, and then we would lower the MTU down to some value. But again, with the DF bit set, that don't fragment bit set, we have to shrink the size of the IP packet to accommodate those 24 bytes, because again, 1476 plus 24 gives me my default IP maximum transmission unit of 1500. And so when we start to go over 1476, when we're going through the tunnel, the router says, well, you set the DF bit from the command line, so I'm not fragmenting it, I'm going to drop it. And so what's bad about fragmentation? Well, remember that fragmentation is going to hit the CPU, right? And that's an intensive process. In this environment here, not a big deal, but when we're talking about hundreds of millions of packets being routed through, you want to try to make sure that you're not doing a bunch of fragmentation, or else you could see a hit on the CPU having to deal with all of the fragmented packets. All right, well, this is going to wrap up Discovery Activity 2, and now we're going to start to transition into the use cases, or I should say the trouble tickets, where we get to start to use the tools that we've learned so far to troubleshoot Layer 2 and Layer 3 issues. All right, thanks for watching, and I will see you guys on Thursday night.